Okay, so today we're going to talk about Newton's universal law of gravitation. We've already talked about it once this semester, back when we talked about the force of gravity when we were reviewing forces. And for those of you that had me in Physics 11, we talked about it back then too, when I first introduced the force of gravity to you. So for some of you, this is 3 times. For those of you that also have me in Science 12.2, we talked about it there, so this would be the 4th time. So a lot of you, this is going to be a little bit of a repeat. But when we talk about Newton's universal law of gravitation, we're talking about the force of gravity. And it was Isaac Newton that figured the force of gravity out to our understanding of how we have it today. Now, there's that tale of, he was hit in the head by an apple when it fell from the tree. Well, I don't know if he was really hit in the head by an apple, but at least as apples fell, it caused him to wonder, why are they falling? Because he knew that an object wouldn't just move, there had to be a force acting on it, but he couldn't see any force. And back then, people were really good with the forces that they could see. When someone pushed someone, hit something, like that was a force, and so they could cope with that. But the Earth wasn't touching the apples, so why were the apples falling? So Newton's universal law of gravitation suggests that all objects attract each other. It's not just the Earth pulling on the apple even, or the Earth pulling on us when we step off our bed in the morning, or when we step off a chair and it pulls us down. It's all objects exert a gravitational force of attraction on every other object in the universe. How big that force is depends on how big the objects are and how far away they are. Okay? The further away they are, the tinier the force is going to be. The smaller they are, the tinier the force is going to be. So it's directly proportional to their masses, and it's inversely proportional to the distance between them. It's actually inversely proportional to the square of the distance between them. So you would have seen this already from me earlier in the semester. His universal law of gravitation is G m1 m2 over r squared, where m1 and m2 are the masses of the two objects, and of course mass is measured in kilograms. R is the distance from the center of one object to the center of the other. Distance from center of one object to the center of the other. Okay, now it might not be a big deal if we were using 2 of you, if we were measuring center to center or outside edge of your tummy to outside edge of your tummy. There's not a lot of difference. But if we're talking about the gravitational force of attraction between you and the Earth, it's going to matter if we measure to the outer edge of the Earth or the center of the Earth. So we always say center to center. And then the capital G is the universal gravitational constant. Universal constant means it's the same. Universal means it's the same no matter where you are in the universe. Okay? So whether you're here on the surface of the Earth or at the top of Mount Everest or on the International Space Station or on Mars, the G will be the same value. And it is 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared. If you look at the units, then when you put it in the equation and multiply it by 2 masses, the kilograms will cancel out, and then divide it by the r squared, the meters squared will cancel out, and you'll be left with newtons, which is what Fg should be measured in. And so then Fg is the gravitational force of attraction between the two objects. Okay? Another name for it is the object's weight, when we're talking about the pull of the Earth or the pull of whatever planet. Okay? And that's what we did earlier in the semester. If you remember, we picked two people, we put their masses in here, we figured out how far apart they were, and we calculated the FG, and we found out it was like minusculely tiny. And so then we traded one of them in for the Earth. So we used one of your masses and the mass of the Earth. And we filled the numbers in again. And we got something like, if your mass was 70, we got something like 600 and, I don't know, 80 something. So that it was significantly bigger. So we are putting a force of attraction on each other. But it's so tiny, because our masses are so tiny, even if we're only a meter apart, it's still tiny, so tiny that we can't actually notice it. So although each of us are putting a force on each other, we don't feel it. And so obviously, if we're putting a force on someone on the other side of the world who's even further away, they can't feel it either. But when the Earth, one of these masses becomes the Earth, then all bets are off. It's much bigger. If we take a look then at this equation, Fg equals gm, and if we say this is the mass of the Earth, and this is one of our masses over r squared, and we said you could find the weight or the pull of the Earth on either any one of us, all we'd have to do then would be change my mass for your mass for someone else's mass. Because as long as we're all at or near the surface of the Earth, the G is universal. It isn't going to change. The mass of the Earth is the mass of the Earth. And if we're all the same distance from the center, the R isn't going to change. So all of this, when we're at or near the surface of the Earth, is actually a constant. Mass of the Earth is 5.98 times 10 to the 24th kilograms. And the radius of the Earth, and in your textbook, looking for where I put your the textbook. In your textbook, there's a chart on the back. I think it's page 593, 953. I think it's 953. There's a chart with the mass of the Earth, the radius of the Earth, the radius of the Earth's orbit, all of those things. I'm just double checking the page. 955. Okay? And so this chart will come in handy in your life. All right, and so if you were to look in there, you would find the radius of the Earth is 6.38 times 10 to the 6th meters. So if we fill these numbers in for the gm over r squared, we get a number that is very close to 9.81 meters per second squared. When we're at or near the surface of the Earth, then we replace this gm over r squared with little g. And this little g is called the acceleration due to gravity. It is also known as the gravitational field strength. Gravitational field strength, which I'll talk about in a minute. Okay? And so at or near the surface of the Earth, it's 9.81. But anywhere else, it still has a value. It's just going to be different. The further you are away from the center, like if you're at the top of Mount Everest, this R gets bigger, which means your 9.81 will be smaller. If you go to the moon, well, the radius will be different and the mass of the moon will be different. And so there'll still be a little g. It just won't be 9.81. Okay, so there'll still be an acceleration due to gravity or a gravitational field strength. Now, what do I mean by a gravitational field strength? A field in physics is an area around an object where if another object enters into it, it'll experience a force. So if you imagine that this is the Earth, there is an area around the Earth where if you are in that area, you're going to experience a pull down. And because there's a force, then you're going to accelerate downward. How quickly you accelerate depends on how big that force is. So the closer you are to the Earth, the bigger the force will be and the faster you will accelerate. So the gravitational field strength is really just the acceleration due to gravity, and it's telling us about how quickly you're accelerating towards the other object that's putting a force on you. So tonight's questions are going to be with the big equation, gmm over r